Cameras working today?
Anyway, that's why I'm here. Enjoy.
John left hand at the door. Okay. Right, guys. We're coming to the end of analog neural networks. So if you're completely baffled by what's been happening so far, don't give up, because after today we'll be starting on something new, which is digital neural networks. And they are conceptually a lot easier if you can remember anything from year one logic design. There's a lot of similarities there. Okay, just a brief summary because I want to crack on. And I turn this damn thing off. Yes. The problem we hit a couple of weeks ago was linear inseparability, where in pattern space you have two sets of data which cannot be separated by a linear surface. Take it down to 2 dimensions so we can see what's going on. In 2 dimensions, the linear surface is a line. If we have a perfectly acceptable problem that is linearly inseparable, here are my 2 dimensions which I can draw out. If I have a cluster that looks like that, call that cluster A, and a cluster that looks like that, cluster B, completely disjoint, no overlap, separate patterns in A and B, but of course there isn't a straight line that separates. We need higher order terms. Like an equation, a linear equation is y equals mx. It's a straight line in 2 dimensions. But a curved surface would be y equals x squared, mx squared, plus z x1, x2. Higher order term. And of course, that's only the 2nd order. You can go to the 3rd order, it goes higher orders as you like. Going to that exhaustively expands the dimensionality quite dramatically. So we can't have exhaustive machines. So we then went to a fine machine where we took our data, where that is the inputs, we passed it through a transformation network, and this has to be non-linear, or have some non-linear terms. That has outputs which you can control as the designer. You can determine how many outputs come here by the number of terms you're using in this transformation network. And once you've got that, it can go into a linear discriminator, and hopefully we can solve the problem. So that will be the fine machine. Its weakness, of course, is its trial and error. How do you determine the non-linear map? So the next step was, hey, this is artificial intelligence. We're talking about learning things. Why don't we let the network learn the non-linear transform? And that leads to a multi-layer system. And in a multi-layer system, if I take inputs A and B, they can go to, I'll draw these as complete neurons, 1 and neuron 2. The inputs go to both of the neurons. The outputs of those neurons is the transformation. And I think in the notes last week I called this D1 and this D2. Now, if this first layer can learn a suitable nonlinear transform, so the data coming out on D is linear, we can then apply the 3rd neuron to solve the problem. And that would be neuron 3. So that was the idea. And we used this to solve the XOR problem. I'm very briefly going through the XOR problem. XOR is a fun problem. I will stick to the logical XOR, where I've got A and B, and 0 and 1, 0 and 1, and this is going to be F equals 1, and that's going to be F equals 1. This point is going to be F equals 0, and that point is going to be F equals 0. Does everybody understand how I go from a truth table to that two-dimensional space? If not, shout and I'll explain.
Can you explain this?
Right. A, B, and F. This is the truth table. Inputs, 2 inputs, 4 states. The output F for an exclusive OR function is 0, 1, 1, 0. The inputs A, B become 2 element vectors. So I equals A, comma, B. A dimension, B dimension. So this point, 0, 0, where F is 0, is going to be A equals 0, B equals 0, it's going to be that point there, right? This point is going to be A is 0, B is 1, 0 is 1, F equals 1. So I've simply labelled the outputs on those axes. And of course, come what may, I can't have a single line, and also it needs bias because I've got a pattern of the ocean, so that's assumed. But there's no line that will have the reds on one side and the blacks on the other side. So, the solution to this is a multi-layer system such as this, and we can put in a couple of decision surfaces which are represented by what neurons 1 and 2 do, and let's choose them to have the minimum number of errors. If I put a surface down there and said this side is F equals 1, this side is F equals 0, that would have 2 errors. But if I choose a surface here, call that D1. And I think in the notes last week I had that as the positive side and that is the negative side, assuming F equals 1 is going to be positive and F equals 0 is going to be negative. That would give 1, 2, 3 patterns correct, but this one will be wrong. Do you follow that, everybody? On the positive side, F equals 1, positive, correct. On the negative side, F equals 0, F equals 0, correct. But this one down here at points 0, 1, this one here is on the negative side of the surface, but it should be a positive response. F is 1, positive. So that's the best I can do with D1. Let's put another surface in, D2. And again, I'll label this side positive and that way side negative. That's what I used in the last lecture. It doesn't have to be that way. I can have surfaces coming down here. There's many different surfaces you can put in. This is just one example of the solution. Right. Having got that, I can now plot the decisions at this point in the two-layer system. I can have a look at this space, D1, D2 space. And if I plot that out, this is going to be D1, and this is going to be D2. They will pass through a threshold on the output of the neurons, but let's, at the moment, for simplicity, just label the inputs plus or minus. And so this can be minus, and that can be plus, that can be minus, and that can be plus. And what we're now doing is looking at the positions of A and B through the transform of D1, D2. So if I were to label these terms inputs 1 or 0, 1, 2, and 3, just so we know where we are, this is going to be pattern 0. 0, 1 is going to be pattern 1. 1, 0 is going to be pattern 2. And 1, 1 is going to be pattern 3. Right. Pattern 0. The decision for D1 is minus. So that is going to be minus. The decision for D2, the way I've labelled them, is also going to be minus. So this pattern here becomes the pattern at the origin there. So that's pattern 0, and that is F equals 0. For pattern 1, A is 0, B is 1, there is pattern 1. For this surface, forget about D2, for this surface, it's on the negative side. And now for D2, it's on the positive side. So that will be negative D1, positive D2. And so pattern 1 goes there. And it is F equals 1. For pattern 2, up here, A is 1 and B is 0, is pattern 2. And for D1 it is plus, and for D2 it's on the negative side. So that is going to be plus and minus, and that is going to be pattern 2, keep it red. And that is going to be pattern 2 is F equals 1. And finally, for pattern 3, which is over here, whoops, I've got this as well, haven't I? Yeah, should go this side. There's 2 others as a element. Minus plus, double change the others. Now for pattern 3, it is minus for D1 and minus for D2. It's going to be there. And so we're going to have pattern 3 there, and it's also going to be F equals 0. That is a single point. Right, now looking at that, we want to separate the F equals 1s from the F equals 2s. It's linearly separable. There is your surface D3, and if I want 1s to be plus and 0s to be minus, that side will be the plus side, that will be the minus side. We've solved it. The system has learned a non-linear transform to solve this actual problem. So that is good. The problem is soluble, unlike Minsky and Papert in the 90s who said it couldn't be solved. But they hadn't attended my lectures in level 1, otherwise they wouldn't have been so stupid, would they? Right. Okay. Now let's have a look at problems. Right, let's have a look at this block diagram for the outline of the structure of this actual solution. Can anybody suggest a problem we're going to have from what we've learned about these next so far? Yeah.
You're going to need a neuron program.
Yeah. No, because I've got a third neuron there, both connected to 2 inputs. No. How are we going to set it up? How are we going to train it? Well, the training algorithms you've got so far are for a single neuron. Yep. And what we need to do know for a single neuron is we need to know what the output should be and what the inputs are. And we change the weights to get the right output we want. In this system, we've got D1 and D2. It's often referred to as a hidden layer. And we don't know what the heck we need on D1 and D2. Because if we did, we'd use a fire machine and put the transforms in straight away. So we don't have access to the values of D1 and D2 in training, which is a problem. Because D1 and D2 are the outputs for the first layer, which we need to change the weights using heavy learning. And D1 and D2 are the inputs to the second layer. And we need those to train the second layer. So our training algorithm as it stands won't work for multi-layer systems because we have no knowledge of the hidden layer. And again, in biology, the hidden layers, we're not conscious of them. In your brain, you're taking an image through the eyes. We're having an output through the fist, if you like. But I've no idea what goes on between the image of your face and my action. I'm not conscious of the intermediate layers. We have no access to that data. So that's a big problem. And that again screwed up progress in neural networks in history. And it took about 20 years for a couple of guys, an American and a Japanese guy, to sort out the problem of training this. And they developed an algorithm which is quite complex. And I won't be going over it in this lecture, but it is known as error backpropagation. Or for short, backprop. And what this does is it takes the inputs of the first layer and the output of the second layer, and it modifies all the weights in both layers to minimize the error. So we've still got this heavy learning idea, make a change to improve things, but it's done over all the neurons at the same time. And so that is, if you're using multi-layer nets, you would use a backprop algorithm, and if you want to know how it works, go online, because it would take me 3 weeks to explain to you. It took the Americans and Japanese 20 years. And we understand better now. So that's the first problem, the training. And remember, the process is again going to be iterative and recursive. Go through the training set. If you've made a change at any time during that pass in the training, got to go back and check that the previous patterns haven't become errors. So round and round and round again in the training algorithm. So that's one big problem, and the solution is that algorithm. The second problem is the structure of the net. Now, how many of you have used a neural network piece of software? None. Okay. Well, if you do, it will ask you how many inputs do you want. Obviously, it depends on the problem. If it's a picture, it's going to be millions of inputs. If it's a set of measurements, it could be half a dozen, 10 maybe. The next thing it will ask you is, how many nodes do you want on the first layer? And that is a guess. Nobody knows. And you might say, oh, I've got 10 inputs. Let's go 40 nodes on the first layer. The next thing is, how many layers do you want? And that is an unknown. And so the structure of the net is vital to the system being able to work, but it's impossible to specify up front. And of course, what you can do is over-specify the system, because an over-specified system, more nodes than you need, will implement simple functions. But if you don't have enough nodes, it can't implement complex functions. And to give a simple example of that, I think I mentioned it last week, if I take an AND function, if I want to implement with neurons a simple two-input AND gate. So yes, a single neuron would implement that because we know AND is linearly inseparable. You could actually generate the weights for that. But if I wanted to implement a parity function, I'd need much more than a single AND gate. And if I took a very complex system, I took a number of gates here, common inputs, and I put an AND gate in there, a gate in there, to keep the general gates. Put another gate in there. Put another gate in there. And I wanted that to implement the AND function. It could do it. What would all the gates be for that whole system to implement AND? They all have to be AND. So an overspecified system will implement simple functions. We can't go the other way around trying to implement complex functions excuse me, with structures that are simple. And it can become surprisingly complex. Because if I take the parity function, if I were to take a 3-bit parity, you should remember from level 1 that the 3-bit parity function, let's say it's odd, A, B, C, F is going to be 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And for odd parity, it is going to be 1, 0, 0, 1, 0, 1, 1. And if you put that on a K-map using conventional logic design, we put that onto a K-map, you come to the horrible conclusion, F, A, B, and C, 0, 0, 0, 1. What comes after 0, 1? Thank you, thank you. 1, 0, 0, and 1. And if I put that function on a K-map, it is going to be 1, 0, 0, 1, 0, 1, 1, 0. At which point in level 1 we cursed, it doesn't minimize. And how many nodes, how many functions do I need on the first layer of a canonical form for that K-map? 4. So if I wanted to learn 3-bit parity using a neural network, I would need 4 nodes on the front layer. 3 inputs, A, B, C, connected up. There it is, and this is where all the connections come from. Remember the photograph I showed you of the first hardware neuron, 1950 at Princeton? There was a hell of a lot of wires in it. And the output node would be, in fact, the OR gate. So that would be the minimum structure for a 3-bit parity function, which seems fairly complex. But of course, it gets worse because no parity function minimizes in logic design. And if I were to take 4-bit parity, 4 nodes. If I take 4-bit parity, how many nodes on the first layer? 8. If I take 5-bit parity, how many nodes on the first layer are needed? 10. What a stupid number that is. Decimal is no good to anybody. 60. How about 16? Now for the smart ones, n bits. No. No. 2 to the power n minus 1. Check. 4. N is 4. 2 to the 3, 8. 5. N minus 1 is 4. 2 to the 4, 16. So if you wanted to design a neural network to learn the 16-bit parity function, it's not a simple, difficult problem. One, 2, 3, 4, 5, 6, 7, 8. Got to halve those. There's a word in there. 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0. There's an example. Can we recognize whether that's odd or even parity just by looking at the data? Now imagine you're not a human, imagine you're a primate and you're training an animal to recognize odd parity. It's quite a difficult problem. We can't do it by recognition. We, being intelligent, have got a higher level algorithm which is called counting. We would count the ones. But just looking at that by inspection and giving a response to indicate whether it's odd or even parity is quite tricky. Now we could train a network, and in this case we're going to have 16 bits. And to get a network structure that will support that function, we're going to have 16 inputs. How many nodes on the first layer? 2 to the power 15, which I think when I calculated it was 32,768. Now, nobody in the world, starting off, if they were stupid enough to try and solve this problem with a neural network, would start off with a simulator, or inputs 16, how many nodes do I need on the first layer? 32,768. No way. That's what you would need to learn that function. So, we've got a problem. But problems always have solutions. What did we do in logic design to solve this 16-bit problem? We didn't build a canonical form that had 32,000 AND gates on the top there, did we?
Don't cares?
No, don't cares. Parity is fully specified. We used a cellular structure. And the cellular structure doesn't take the full input. And the cell structure might be A and B. We would have a node there which would learn the partial solution on A and B. Then we would take that to another node where we could take another bit of information in. And that would give A, B, and C. And we can carry on adding additional layers which are taking a little bit more information and generating partial solutions and refining them until we've got the whole solution. And again, if you look back in your notes or memory of level 1, which you can't even remember living through, we discovered that instead of needing 32,000 AND gates, if I was using a cell structure, there would only need to be 15 gates, because each one we're doing a partial solution and adding a bit more information. And that is the principle of what is known in neural networks as deep learning. You are learning features and you are adding to those features. And that can lend to simpler solutions. So, those are some of the pitfalls for budding entrepreneurs wanting to use neural networks. And the key thing here is to try and understand what the problems are. So, how are we doing for time? I've got one more topic to discuss on analog nets. So far, the main thrust of the applications has been learning to recognize patterns, to separate vectors. There is another role of a neural network. And this is slightly harder to achieve than recognizing data sets. We are using neural networks to represent or to model functions. But what's the point of that? Okay, 20 years ago, American Air Force, their super F-35s or whatever, go pretty fast. The pilot can't think fast enough to work out what's going on. They need some flight assistance. The aircraft has 10,000 parameters which can be measured. They can fly the aircraft when it's safe. Use those pattern data to train a neural network. And the key thing in function approximation is you are not trying to find a decision surface that divides two classes. You are trying to find a decision surface where all the patterns fit on. So the only data you have when the system is functioning correctly is points on that decision surface. And it's bound for complex systems to be pretty nonlinear. So that's the idea behind function approximation. So if you imagine a system which you are monitoring and you have points like that, this is your data when the system is functioning correctly. And what you want to find is a weight vector that defines the decision surface on which all those points lie. So there is the line, there is the line up there, and that will be defined by a weight vector somewhere else. And clearly, apart from the simplest problems, it is going to be nonlinear. So that's the idea. Functioning correctly. F equals naught, or S equals naught, the output of the network. Malfunction. S is not equal to naught. And that can sound an alarm, whatever. Now, it's not only used for monitoring aircraft, it can be used for industrial plants. You've got a manufacturing plant that's producing a product. It has various rates of output. Sometimes it goes fast, sometimes it goes slower. What are the conditions for optimum control of that plant? And again, if you can find the surface with a neural network that represents that model, then you've got a solution to the problem. Again, becoming simpler than car owners, using it for detecting the driver of the car. Now you drive? You drive, you've got to throw out everything, yes, I've seen that driving. Right, you drive, you've got driving habits, you're very cautious, you observe the speed limits, you slow down at bends, you can measure all those parameters, not very much acceleration, whatever. He goes and steals your car. First thing he does, a few donuts in the car, boom, foot down, wheel spin, spinning crazy, heavy braking. Completely different set of characteristics. Now, if I can take a neural network, taking 100 measurements from your vehicle when it's running, for you driving, and find the equation of that, and then when you're driving along the road, F equals naught, it's you. And he goes in and has a good time with your car, immediately we're way off this decision surface, and we will get a response somewhere over here. It's not on the control surface. Immobilize the car or whatever. So again, it's a possibility. Coming down to machine tools in manufacturing, when machine tools, robots are being used, lathes and things like that, as the tools wear and whatever, if you've got a control surface or traffic condition, if something has gone out of spec or whatever, then can a neural network detect? So that's the idea of a function approximator. And we have a training algorithm. And it's a modification of the error correction feedback. So it shouldn't come as a surprise to you. Training. Right. and we only need one data set. And that is the data set from you driving your car. Right. Choose W in the normal way. Random initial weight vector. Input first pattern. So we are going to have W dot I. That will give you an output. Now, because we're doing a function approximation, the input, we're not looking for a positive or a negative response. We are looking for a zero response. So, if S is 0, no action. The weight vector is perfect for that input pattern. And that is very unlikely, because in the previous case you had the whole of pattern space. It only had to be one side or the other side of the decision surface, and 50-50 it was right or wrong. Chances are half the patterns would be correct. When you're looking for a pattern to be on that surface, it's got to be one pattern on one of these lines. The whole of the other space is errors. So that could happen, but it's unlikely. Now, if S is positive, or S is negative, error. And we need to do some error correction. We need to update the weight vector the same way as we did before to W prime equals W plus Ci, a fraction of the input pattern, such that W prime dot I, the updated weight vector with the current pattern, equals what? It's got to be correct. 0! That is the difference between the function training algorithm and the pattern classification algorithm. In the previous algorithms for pattern for data recognition, we would make this equal to minus S. The original error put the opposite sign to correct the error. This time it's got to go to 0. So, substituting for W prime in that equation, we get a W prime is W plus C dot I, W plus C I dot I equals 0. Previously it was minus S. W is the original weight vector, I is a pattern error, the only unknown is C. So expanding it out, W dot I plus Ci dot I equals 0. But W dot I was the original error, which was up there, fourth line down, S. So that is going to be S plus, oops, if it was right, S plus Ci dot I equals 0. That was the original error. This is the correction factor. That is what we want. C, therefore, is going to be equal to minus S over Ci dot I. And so, let's see, yes. So that is the update correction factor. And how does it differ from the previous example? The previous correction factor for pattern recognition was C equals minus 2S over that. So that is the difference. And instead of bringing the error patterns to the other side of the decision surface, you are bringing them onto the decision surface. And that's the update factor. Right. One example of using a neural network as a function approximator.
Sorry, the correction factor brings the what to the
The previous pattern, the pattern I, which was wrong, instead of taking it, instead of taking it from one side of the surface to the other side, you're taking it from the point which is not on the surface to being on the surface. So, if I've got a pattern there, if I have that one there, this is the plus side, this is the wrong pattern. I move the weight vector so that this pattern is on the top side. The weight vector, remember, is over here. I move that weight vector, this will come down. If I move it to this position, so I'm moving W to that point there, we move the weight vector, and this now is on the same side, the correct side of the surface. That's for recognizing patterns. For function approximation, I move the weight vector. Let's have a pattern like so. There's a weight vector W. I've got a pattern there. I want that to be on the decision surface, so I have to move the weight vector so it moves the decision surface so that we get a pattern, bang, that's on the surface. And that will be the updated weight vector. So instead of moving it to the other side, you're moving onto the surface. Right. What's the time? 10 minutes to go. Quick example. And the example I'm going to use is a speed monitor. And again, I'm taking two measurements. I'm taking the measurements of distance and time. And let's have this in miles. And let's have this in minutes. Keep the numbers small. And let's put some scales on here. Distance. 1, 2. And let's have 1, 2, 3, 4. Right, so for 30 miles an hour, one mile takes how many minutes? 2 minutes. So at this point 2. So that would be 30 miles an hour. Give me another point, 2 miles. 4 minutes. And of course it will go to the origin. Because as you tend to 0, then the function will go to the origin. And that is the straight line at 30 miles an hour. Okay, now the model for that, a neuron model. So we're going to have one with distance. The other input is going to be time. And we'll use a single neuron. I'll draw it out as weights and summer. And what distance? So those are the connections, and they go into the summer, and that's your model. This will be W1, this will be W2. In this particular example, we don't need a bias because the function goes through the origin. You don't need to offset it there. So no bias needed. And because it's a linear function, I only need 2 points. But I'll take the origin, that's the easy one. So the training data will be distance and time, 0, 0, and let's take this point 2, 4. And we need an output of 0 from this network with this training data. Concentrate on this one, 2, 4. Remember, it's going to be W1 times 2 plus W2 times 4 equals 0. Can anybody estimate values of W? Okay, 2. Give me a weight.
1.
A bit more interesting than that. 2. Plus 2. Right. 2 plus 2 equals 4. Sorry, 2 times 2 is 4. Plus W2 times 4 equals 0. Minus 1. Those are your weights. That will define that straight line. So the weights go in there as plus 2 and minus 1. Give me another set of weights.
4 minus 2.
4 minus 2, 35 minus 17.5. Again, millions of solutions. And what happens? You're speeding along in your car. What happens if I'm in this region here? I've done 2 miles in 1 minute. I'm doing 60 miles an hour. So 0.21. 21 with this weight vector. What's the output going to be?
Not 0. Not 0.
Not 0. What value? Plus 3. It's going to be plus. So it's going to be in this region, positive. And supposing I'm dawdling, supposing I do 1 mile in 4 minutes, that is going to be 1,4. What response do I get for that input pattern against that weight? Negative. Right, so this is going to be the negative side. So what have you got when this is running? This is 30 miles per hour. This is too fast. And this is too slow. And you've learnt that without any Newtonian dynamics equations. You've simply learnt it by setting, by a random process of adjusting the weights, it's learnt what 30 miles an hour means. So there's an example of a very simple function that can be approximated with a neuron. So, jet aircraft, motor cars, human behavior, and all the interesting problems where you might want to do this modeling is much more complicated and it's almost certainly going to be non-linear. But that is the principle of the neural network learning a function. Okay, let me summarize now. I've got 5 minutes, 3 minutes left. That's really all I want to say by way of analog neural networks. So just some points, bullet points, should they come up in the exam. the names we've used. The first examples were called McCulloch and Pitts neurons. The original ones were also called linear discriminators. They are sometimes confusingly called binary pattern classifiers. And I think that's a very confusing name because it's not binary patterns, it's binary classifiers. The patterns can be analog, but the classification is plus or minus, it's a two-class classification. So beware of that one, that's somewhat misleading. When they were used to approximate logic functions, they were called threshold logic units. And nowadays, in the neural network world, the term that is used most commonly to describe these is that made-up word, perceptrons.
So what's the first one? McCulloch and what?
McCulloch is the guy, and the other guy was called Pitts, his mate. He was the Pitts. So those are all the same principle. No, but if you come across them, you know what we're talking about. In the exam, for a single neuron, I tend to use McCulloch and Pitts, and I might, for multi-layer perceptron, multi-layer systems, I will use perceptrons. But the other textbook will use them. What are the unresolved problems so far that we need to sort out? So those of you embarking upon PhDs and Nobel Prizes, these are the things to work on. The big problem still is training. The training is recursive. It means when you've trained gone through the training set once, you've got to go back and do it again if you've changed the weights. And that can lead to endless processes. It can take hours, it can take days. And of course, if it's linearly inseparable, or you don't have enough nodes in the structure to support the function, it will go on forever. And you don't know if it's ever going to conclude. If that's the case, people will say, well, it's got 90% of the training set correct. I'm going to flog this as a device, and the best accuracy it's going to have is 90%. Beware, it will go wrong sooner or later. The other thing that really bothers me about this modeling is we're trying to copy natural systems, we get inspiration from natural systems. And clearly in human beings, we do not have this recursive training process. When I see you for the first time, I've got your face. You're smiling now, you're looking pretty miserable when you get your own questions. I recognize you. I don't have to keep going smiling face. I don't have to spend a minute or a day or a month thinking about you to get your face. I recognize you straight away, as I do you, and you. Certainly you, yes, to get to know one stuff. So this training method is not biologically plausible. Humans, animals don't learn like this. So although it might be useful for engineering, it's not a solution of human intelligence. So the training is still the problem. And the next big problem is the network structure. How do you specify the network for a given problem other than by a random process? And I reckon if you can solve either of those problems, I'd give you a Nobel Prize. They are big, big issues. So that's pretty well all I want to go by way of introduction of the analog net. We'll now next week move on to digital nets, and digital nets are superbly better, partly because there's a lot of work going on with them at Brunel, and we've got an exhibit in the Science Museum of the first system that really worked about 30 years ago. But it has, by using a digital function, the training is a single pass through a data set. And just to give you an inclination of how this works, if I'm dealing with binary data, just take two examples of a 3-input function. If I want to recognize 0, 0, 0 on A, B, C, F equals not A and not B and not C. F goes 1 when A is 0 and B is 0 and C is 0. You all agree? If, however, I have a choice of patterns, you know, look at you move your head, and 0, 0, 0, oh yeah, your glasses come in, 0, 0, 1, it's still you. If I want to include choice of patterns at the sampling site, if I want to recognize 0, 0, 1 as well, I change the logic function, it becomes not A and not B and C. Forget about the minimization, the India told you to ignore it last year, me having taught you all about it in year 1. But the key thing of that is, it doesn't forget the response of 0, 0, 0. I've changed the function, and this function, of course, will give f equals 1, whether it's 0, 0, 0 or 0, 0, 1. And that is so obvious and so simple, but it is so important in training digital nets. So we only need a single pass through the data set. So instead of training for hours, days, months, or years, we train for microseconds. And that's what will come, not next week, but the week after. Anybody got any questions? Hang around and I'll talk to you.
Yeah.